Okay, today we're going to talk about the concept of pH, which is something I'm sure you've heard of before, but probably don't really understand what it means. We're going to try to fix that. Okay, if you take a pure sample of water, there's going to be a few water molecules that will actually interact with each other. Okay, it doesn't happen very often, but when you have hundreds of trillions of different atoms in there, every once in a while, one water molecule will steal hydrogen from another water molecule. You'll get a hydronium ion and a hydroxide ion.
Water is not water anymore.
Water is not pure H2O. No. Now this is happening in what's called dynamic equilibrium. Every once in a while, one of these, two of these will react and make these two things. But every once in a while, two of these things will come together. That hydrogen will transfer back over, and you get water molecules left. So this is in equilibrium. Okay? If we were to look at the concentration of hydronium ions and hydroxide ions in that water, what we would find is if you had pure water, the concentration of H3O plus is going to equal 1 times 10 to the negative 7th molar.
Very small.
Very small concentration, yes.
Why is that?
A tiny little bit. Just because water molecules are pretty happy just being H2O. So it's just a few of them that every once in a while will have a hydrogen that's transferred. And a lot of those are going back the other way in that equilibrium. So if you were to take a whole bunch of water molecules, you would find that very few of them, just a few, would be in this state of hydronium and hydroxide.
Well, kind of like how humans are just have to be an average Joes, and every once in a while they do.
Okay. Now, again, a lot of times what we do is we just kind of blow by the fact that it's actually in a hydronium state. And what we'll actually see is it put like this. The concentration of protons, concentration of hydrogen ions, H plus ions, is 1 e to the negative 7. So even though we see this most of the time, we need to remember that it actually means hydronium. So that's something to kind of keep track of. Okay. Now, if the concentration of hydronium is 1 times 10 to the negative 7th, it stands to follow that the concentration of hydroxide also has to be 1 times 10 to the negative 7th. And that's because every one of these that was created has to have one of these that was created. In the reaction, we have 2 water molecules. If we get out a hydronium, you have to get out a hydroxide too. So in pure water, these two things are going to be equal to each other. They're both going to have a concentration of 1 times 10 to the negative 7. Okay? Now, using those numbers, 1 times 10 to the negative 7th, can be a little bit clunky. So we've come up with a way of expressing that in a little bit easier terms, and that's where the whole pH comes from. For pH, we take the negative log of the concentration of H plus ions. So what we would do is take the calculator and we go negative log and then put in 1 e to the negative 7 and hit equals. So what do you get if you take the negative log of 1 times 10 to the negative 7th?
Number.
You get 7. Okay, that's the way logarithms work. The whole point of a logarithm, a base 10 logarithm, is you're taking basically the exponent of the times 10 to whatever exponent, and you're bringing it down. Because we have a negative exponent here, we have to have the negative log. So pure water has a pH of 7. Okay? But
Seven's right in the middle.
it's not spectacular. I'm saying that's what pure water's pH is, because the concentration is 1 times 10 to the negative 7.
Neutral.
That would be neutral, right? We're going to look at that chart in a minute.
Can we test the pH of water? Yeah. With pH strips.
Actually, make pH strips.
Are we going to test the pH of our milk? Like the pH of your saliva?
It's going to be acidic.
Too. Let's say we add some extra hydrogen ions. Okay? So we're going to put in an acid, and it's going to add a whole bunch of, it's like HCl, it's going to add a whole bunch of extra hydrogen ions.
And that goes up, right?
So that's going to increase this number. It's going to increase it because we're getting more and more hydrogen ions. Oops, not this number. Sorry, this number over here. So by adding an acid, let's say we get the concentration of hydrogen ions to 1 times 10 to the negative third. Okay? Now realize, this is a bigger number than this, right? There's a lot fewer zeros in front of that one between the decimal place. So there's a whole lot more hydrogen ions in here. How many times more hydrogen ions would there be in there?
4? No. 48,000. 10,000.
It would be 10,000. If we were to write out these numbers, this one would be, oops, and this number right here would be, so you see there's huge differences between those two numbers. That's a big change. This is 10,000 times more concentrated than this. So what would be the pH of that?
14. And
Good lord.
70.
Not even close.
700.
8.
What do you get when you take negative log 1e to the negative third? You get 3.
Close.
Okay? So here the pH is 3. And we look at this and then it makes it look like these two pHs are fairly close to each other. But realize, because it's an exponent, again, this is 10,000 times more concentrated. It's 10,000 times more acidic. That's because it's a logarithmic scale. Each jump, or each change in pH, like from 7 to 6, would be a jump of actually 10, because it's a logarithmic scale. So from 7 to 5 would be 100. From 7 to 4 would be 1,000. From 7 to 3 is 10,000. From 7 to 2 would be, anybody? 2,000. No, not 2,000. 100,000. It's times 10 each time.
Just go with the very funny after we graduate.
So, let's try a couple of these for practice. Sorry, that should be a 4. E to the negative 4 molar. So our concentration of H plus ions is 2.76 times 10 to the negative 4th molar. What would be the pH of that solution? What's it? 3.56? Yeah, it would be 3.56. So we would say that the pH is 3.56. Just take the negative log. Okay. Let's do one more. What if the concentration of H plus ions is 5.92 e to the negative 10th?
Either, bud. Last.
9.23.
That's what I got.
What did you do wrong?
You got a fucking carrot thing in there.
Yeah, if you use the E, you don't need the carrot. Okay, simple enough, right?
For now.
Now, if we notice, for this one, 5.92 times 10 to the negative 10, right, that is less than normal water. Pure water is 1 times 10 to the negative 7. So this would have a lower concentration of H plus ions than pure water. And if there's a whole, very few, even less than pure water, that means there has to be some OH ions in there, some sort of basic thing that's snapping up those extra H plus ions, making them very, very low concentration.
So base makes it bigger, and the acid makes it smaller.
Right, because bigger means there is a lot less of them. That's the way the negative logarithmic thing works. A small number means there's a whole lot of them. A big number means there's very few of them. So on our pH scale, okay, well, we'll come back to that in a minute. On our pH scale, anything that is lower than 7 is considered acidic. Anything that is higher than 7 is considered basic. Basically, if you've got a pH that is bigger than 7, we were saying there's extra stuff in there that is taking up those H plus ions. There's less of them than there would be in pure water. There's very few of them, so we have a high pH.
So anything like less than 3 we should not do.
Well,
Drink soda.
You probably shouldn't drink battery.
I said less than 3.
Well, I mean, we've got stomach acid, but saliva.
We don't necessarily need stomach acid,
When you fill it up, it's there.
throw up a little in your mouth.
but that's not very much.
Only bring you throw.
And you don't have a choice.
Yes, the lower the number, the more concentrated those H plus ions are, the more reactive it is going to be.
What's melted magnesium?
It's something that you take for upset stomach. It's magnesium hydroxide is the formula for it. By adding those extra OH ions, that basic solution, you're trying to neutralize the acid in your stomach. Okay?
We drink some ammonia, it looks like. We drink hydrochloric acid.
Drink some sodium hydroxide.
We drink battery acid.
So, this shows our hydronium ion concentrations, the actual numbers, and then the exponential notation, and then the pHs that are correspondent to. So here we see this is neutral, again, fairly, on the wrong one, across right there. Okay, fairly low concentration, we get lots and lots of them. And again, each jump is a jump of 10. We have a low pH. As we go down the scale, we get a high pH. Now, there's a couple of things that we need to talk about. It'll go along with the calculations you're going to do tonight. if you multiply the concentration of H plus ions times the concentration of OH minus ions, you will always get 1 times 10 to the negative 14. Okay, remember in pure water, we said these two concentrations have to be the same, and they were both 1e to the negative 7. Well, if we increase the number of H plus ions, if we increase the amount of hydronium that's there, that's actually going to lower the amount of hydroxide that's in the solution, because there's going to be extra H plus ions to kind of react with that. So if we change the pH to, say, 1 times 10 to the negative 3rd molar, would this be an acidic or basic solution?
Acidic.
Acidic, good. That means there's going to be a whole lot less of the OH minus. And because these always have to multiply to 1 times 10 to the negative 14th,
Divide by 3.
we would divide by 1 times 10 to the negative 3. And we would get 1e to the negative 11th molar. So the more H plus ions there are, the fewer OH minus ions there are. But mathematically, the multiplication of their concentrations always has to get time to 1 to the 10 to the negative 14. Yes?
Does it always work out to where the exponents are added together to 14?
Yes. That's the way the logarithmic scales and everything work. Because if you think about it, if we take the negative log of each of these numbers, we're going to get 3. We're going to get 11. Because we're doing the log, we would have to add those. Oops. 5 to 2. I don't know.
Yeah, I was just wondering if that was simply coincidence or...
Yeah, that's the way it works. And this highlights a point where we have the pH and something called the pOH. The pOH is going to be just like the pH, except we're looking at the concentration of the hydronium ions. So if we have a pOH of, say, 11, right, that means there's 1 times 10 to the negative 11 of the hydronium ions. And the pOH is going to work backwards. If you have a high pOH, that's going to give us an acidic solution, because there's very few pOHs. If we have a low pOH, that's going to give us a basic solution. But the pH and the pOH always have to equal 14. So if I give you the solution, I say the pOH of this solution is 4, what would the pH be?
10.
10. It has to be. And that works with the concentrations, because if the pOH is 4, that means there's 1 times 10 to the negative 4th of those hydroxide ions. That means there has to be 1 times 10 to the negative 10th of the hydronium ions. So those are two things that you can use on your homework for solving those different equations, figuring out how many of each of the other type there are.
So you gotta ask those questions, because Manning, for some reason, can make 3 problems in a row that are the same. Like they add up, like you could use that as a shortcut, but then for the rest of them, I don't know how he does it.
I'm not following you in the least bit.
You know what I mean? No. Well, like you could find a shortcut like that by just like adding the negative 3 and the negative 11 together to get negative 14. And it'd work out like 3 problems in a row. So you kind of assume that'll work out for the rest of them.
No, it doesn't.
But he doesn't say.
So what you're saying is you found a couple of coincidences and tried to make a mathematical law out of it, and it didn't work.
Not a lot, just
Quickly.
yeah.
All right, let's do one practice problem, then you can get started on your homework here.
That's a lot.
Let's say the pH wait a minute. We haven't talked about this yet. No, we gotta learn one more thing. Sorry.
Hey.
We gotta be able to go backwards too. Let's say the pH is 3.76. We need to know what the concentration of H plus ions are. How would we find that? Basically what I'm asking is, what's the opposite of a logarithm?
D logarithm.
No, there's no D logarithm.
It's shift log.
Okay, what does shift log do?
Or divided by 10.
Natural log. I can't remember.
It does something with 10, but it's not timesing or dividing by 10.
It's like putting that.
Right, it puts this into the exponent. So if we want to find the concentration of H plus ions, we take 10 to, because it's we're using a negative log, we need to put the negative in there. 10 to the negative 3.76. Put it up as the exponent. That's the opposite of taking a logarithm. And you do have a button on there. If you do shift log, it will put it in for you, but you also could put 10 with a caret, negative 3.76. And we get the concentration 0.74 e to the negative fourth molar. Don't forget your molarity there. It's all based on moles per liter. Okay? And the same thing would be true for POH. If you know the POH is, whatever, if you want to find the concentration of hydroxide ions, you take 10 to the negative, whatever that POH is. Okay, so that's not too difficult. Here's your practice problem. Let's say the pH is 5.92. What would be the concentration of hydroxide ions in the solution? There's two ways to go about solving this problem. Either one will work just fine. I think one's easier than the other, but if you think you got an answer, I'll be happy to do that.
Well,
No, you're shift log 5 point. Number.
Is that anywhere close?
Nope.
Which
that is way too big.
What you found was the concentration of hydronium. We need to know the concentration of the hydroxide.
What was the number?
Yeah, it's not.
It's right there.
No, what was the number you calculated?
Okay. There's a couple ways to go about it. I think it is easiest. The thing that makes it a little bit hard is we're talking about POH, but we need to know the concentration of the OH minus, right? But one thing that we remember, we know that the pH and the POH always have to add 14. So how do you define the POH?
Your answer is 8.
pH is 6. Nope.
Minus.
Minus, right? Because this and something else.
Yeah.
Okay, so that's the POH. Okay, and we know the relationship between the POH and the concentration of hydroxide ions is the logarithmic relationship. So just your answer with your it's no.
negative 8.
I mean, there's an 8 in the number, but no.
I feel like it's not a complete number. I feel like it's an 8.2. 6.
Oh,
What's that?
I'm reading Nashville. I know there's one that's in there. Because I did not grab a calculator.
That's what we got for the shift log.
Okay, listen.
So we got -6.
We know, well, it's 1.2 times 10 to the negative 6. This is the concentration of H plus.
Charles, is this it?
You have a lot.
We know that this, multiplied by the concentration of hydroxide, always has to equal 1 e to the negative 4. So this times unknown equals 1 e to the 4 negative 4. That was,
Probably not.
yes.
Good Lord, got that.
No, I would put this on the
Oh,
Wait.
yes.
Listen, yeah, this is the H plus ions. We know that this, multiplied by this, has to always equal 1 e to the negative 4.
Yeah.
Something he did this.
That point, oh.
This will be 12 points, or 1.2.
So basically, this, I'm sorry, write this, 1.2 negative 66, times the concentration of hydroxide ions, which would be our unknowns, you can say it's X. Okay, equals 1 e to the negative 14.
Oh, you have your equals 1 in it, right?
Right.
Right.
Two more. I think we came up with an idea.
You,
Yeah.
like that was the decimal.
No,
Negative.
it's a -8.
No, it's
It's a math.
yeah. This is right.
The two things multiplied together equals 1 e to the negative 14.
Yeah.
Yeah. Yeah.
Just Roark.
Which polarity?
Damn it,
Which polarity?
Sorry, my idea was right, but just the way it was wrong.
Please don't be.
Probably.
Okay, now listen. Some of you went about it one way, some of you went about it the other. I want to show you both ways so that you understand the way that you didn't use. Whichever way you want to use doesn't matter. Or, it's up to you. You get the same answer either way. Do the way I would think about it is, I think is the easiest first, but it's not necessarily the right way. We know that the pH is 5.92. And we know that this plus the pOH always has to equal 14. So in that case, I would just subtract 5.92 from 14 and find that my pOH is 8.08. Okay? And now at that point, I know that I can take the 10 to the negative of the pOH to find my concentration. That's one way to do it. The other way to do it is to go ahead and start with the logarithm right here and take 10 to the negative 5.92, which gives me 1.20 e to the negative 6th. But I know this is my concentration of H plus ions, my hydronium. But we know this multiplied by the thing that I'm looking for, the concentration of hydroxide, has to equal 1 e to the negative 14. And so in this case, I can take 1 e to the negative 14 and divide by the 1.2 times 10 to the negative 6th. Either way to do it is fine. You'll get the same answer no matter what, which is like 8 point something e to the negative 9. 8.31. Don't forget your molarity. for you. I don't care how you do. Yes, Riley.
Shush.
So,
It's a light bulb cruising cube.
on your worksheet, I've basically given you the same numbers in almost all cases there, I think, but I asked you some different questions.
Well, that's fine.
So do all those on 14.3 for tomorrow.
Would you, how would you consider, what would you consider neutral as far as how close to north or south of 7 it is?
That's a good question. I mean, specifically neutral has to be like exactly 7. But because we have some rounding error here, I would say anything between 6.9 and 7.1, right, you could consider neutral.
So first C,